Yeah, all right. So listen, everybody, we learned last week that if I gave you feet per second for the y value and x was in seconds, the area under the curve would be feet. And so we know often with graphs, we want to find the area under the curve, which I called capital S, mainly because that's what textbooks do. Because S is a distance usually, right? Especially for physics. I want to be clear then that we can talk about this S, all right, based on what we talked about last week, as the summation of a bunch of rectangles. Do you guys agree? And I can pick how many, right? So there's 3, there's 4, not a good one, 5. So I could say S is the sum of n equals 1 to 6 of, I'm going to call the rectangles A sub n's, where that's the area of each individual rectangle. And those rectangles are typically what? Equal space. Does that make sense to everybody? If you're going to draw them in, we don't draw 1, 1 and 1, 3. They would be equal width rectangles. But I don't want to do that because you know what? That leads to a lot of errors. So what I want to do, all right, is I want to draw in an infinite number of rectangles, all right? And add up each rectangle, we'll call it n sub n. So if we're going to draw in an infinite number of rectangles, can you picture that? I mean, think about it. How we're going to draw an infinite number of rectangles, right? All right. This is where it gets fun. If I'm going to draw an infinite number of rectangles, the height of the rectangle is pretty easy. So I have an infinite rectangle. Say I just picked this one here. This is one of my infinite rectangles. Boom. You guys would agree that that's the height of that rectangle? What is the width going to be of that rectangle? You have an infinite number of them. Approaching 0. Guys, what I want you to see is that the height of the rectangle is f of x. And that the width, and I'm going to call it delta x, means that delta x is going to go towards 0. And all of a sudden, if I say that, what are we thinking? I hope you're thinking limits. You're thinking limits, guys. All right? So I can write that the region S is equal to then the limit as n goes to infinity of the first rectangle, which is f of x1, right? Just whatever height, whatever the exponent values, times this delta x, which is going to approach 0, plus, and I'm going to go down the page, f of x2, the second rectangle, which is going to be multiplied by the width of delta x, plus f of x3 delta x plus f of x4 delta x, dot, 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 till what? Till we get to the infinite, the infinite rectangle, x sub n delta x. And that limit would give us, not only would it be an approximation, that would be the exact area under the curve. You guys agree? Because now, unlike yesterday, or last class period where we had the rectangles being over or under estimates, all these rectangles would fit perfectly under the curve. And you would be summing up all these perfect rectangles. And I'm leaving white spaces just so you can see it. Actuality, if I'm doing this the right way, it is solid blue. Can you picture it? It'd be filling, right? And you're summing up all these rectangles to infinity. Except that's pretty hard for us to do, right? Until you guys start grinding and come back in 10 years, you'd still be at it. Maybe I tell you to go from A to B, and maybe it's 3 to 5. And maybe we want a really close approximation, so we say delta x is 110 million. And this is how computers do it, though. Computers don't do calculus. Computers actually do it this so far out, and they can do so many calculations, it actually does that. Okay? We're not computers, and we're going to do calculus, okay? Now, if we talk then about this, we can't do this, okay? We cannot do this. our ability then for Riemann sums is to not go to infinity. We can do a fixed number of those, okay? We have to get to this, right? And what's our favorite limit? Does anybody know what our favorite limit is when we think about this? I hope our favorite limit is the derivative limit. We'll use h this time and make it easier. I hope you're all thinking that this is your favorite limit. Remember when we had to do derivative longhand? And actually, that's going to become really important when we make the next big step. All right? So let's pause for a second. I'll put up a couple of problems we're going to work. And we're not going to do infinite rectangles because we can't. All right? We're going to do fixed rectangles. All right. So today, I'm going to have a function. It's my favorite, but I've shifted it up too. F of x equals x squared plus 2. And I'm going to estimate the area under the curve from 1 to 3 using 4 rectangles. All right, you won't have to have a picture once you get good at this, but I don't know how. I always draw a picture, even if it's just a sketch for what's happening. So, and actually, guys, I don't draw the whole curve. I find the whole curve makes me confused. I plug 1 in, and I see that the result is 3. Boom, I decide that's 3. I plug in 3. You guys see it's 11? And we all know the parabola is shaped like that. All right, that's the curve. I want to know the area under this curve. You guys agree? And I want 4 rectangles. So the question is, what is the width of one of the rectangles? All right, I'm going to call the width of the rectangle delta x. And I can't stress this enough. I am going to fit 4 rectangles in between 3 and 1. So guys, 3 minus 1 is 2, divided by 4. I think the delta x, the width of each rectangle in this case, has to be 0.5. Right? And picture this, guys. That means there's a rectangle from 1 to 1.5, 1 from 1.5 to 2, 1 from 2 to 2.5, and 1 from 2.5 to 3. All right, awesome. And there's a formula here. You guys see it? The formula here is b minus a over the number of rectangles. You think about it, but I don't particularly like to teach the formula. I think we can see it. So I'm going to put 2 in the midpoint, and I'm going to put 1.5 in and 2.5 in. All right, now here's the problem. I don't know the best way to do this. And I'm going to do it 3 ways, because I didn't tell you, should you use the left endpoint, the right endpoint, or the midpoint, right? We're going to talk about what all those mean, and we're going to go through each of them. So here's what I'll say first. I find it easier personally once I put these 4 rectangles in. And we're going to do it 4 ways. We're going to do it the right-hand method, okay, the left-hand method, and the midpoint method, okay? All right. And I am going, for the simplicity of our time here, I'm going to put these in. I know at 2 squared is 4 plus that is 6. I know at 1.5, 3 halves squared is 9/4 plus 8. This is 17/4. The y value, and I'm putting those in. And then green yet. I know 2.5 is here, and I put in 5 halves squared is 25/4 plus 8 is 33/4. All right. Now, I want to draw the rectangles. I want to draw 4 of them under those curves using the right-hand endpoint. The right hand is here for the first rectangle. There's the first rectangle, everybody. And you notice I grabbed the height of the curve on the right-hand side of the rectangle. The next rectangle looks like that. The next rectangle looks like this. And the last rectangle looks like this. Everybody, overestimate or underestimate? Just looking at it. Over. And everyone, that's because there's this area above the curve that we don't want to get, but it's going to work. All right. I want to be clear about this, and I'm going to skip a step. Guys, what is the width of each of these rectangles? 1/2. So I want you to see it's 1/2 times f of x1, the first height, right? Plus 1/2 times f of x2, right? Plus 1/2 times f of x4. Guys, what's common in all four of those products? Yeah, the width. So when I have these problems, I immediately pull out the 1/2. All right. Now, everybody, what's the height of the first rectangle? I think the height of the first rectangle is 17/4. That is not purple. 17/4. What's the height of the next rectangle? I think the next rectangle is 6 tall. And you see why I'm using the colors, guys, to match the points on the right-hand side? The next one is green. The right-hand value is 33/4. And the last one was black, and it is at, and we know this from the original function, plus 11. Well, everybody, this is a calculator problem. You guys agree? So make those four values and multiply by half. All right? We'll do that. We'll do all the math in a second because that's not as important as what this is doing. And that's called the right-hand Riemann sum because we use the right hand of the rectangles. All right? Kind of pain here, right? Let's get rid of those. And now let's try to do the left hand. Huh? You should do this for days. Yeah, probably in an accelerated course, you probably only get it for minutes. So, everyone, do we agree? For the left-hand limit, it's still a width of 1/2. Does everybody agree with that? And now let's draw. So my first rectangle goes to the left-hand point. The left hand. It goes up to the left hand. It goes up to the left hand. It goes up to the left hand. The left-hand point of the rectangles. Now, what do you notice about this estimate? It's below. It's an underestimate. And again, we'll fill in the values from the table. It's 3. And then it's plus 17/4. Plus 6. Plus 33/4. Huh. You look at the colors between the left hand and the right hand, it's kind of interesting. There's a lot of repeats. The only difference is on the right hand value, we use the right hand 11. And on the left hand, 11's not in it. The left hand value of 3 is in it. What do you notice about the other 3 values? They're all the same. All right? And we know that's an underestimate in this case. That has everything to do with concavity about this curve. This is a concave up curve. All right? Not always this way, okay? I want to take 1 second here and get these values. All right? So I am going to pause the video and just do the calculator and write some numbers here. All right, so we did a couple quick estimates here, and we got the right-hand value is 59/4. We got the left-hand value was 43/4. Everybody, if I'm doing this, I know 59 is an over. I know 43 is an under. I would take the average of these two, all right? And if I average the left hand and the right hand, and I would actually write out that I'm averaging them, I would say that maybe 51/4 would be a good estimate of the area under the curve. Does that make sense to everybody? It leaves one other method we got to talk about today, which is the midpoint method. And this is much more difficult. Well, not difficult, just time-consuming. Much more time-consuming. Difficult's the wrong word. All right, because here's the problem. I put all those values in to help us. Is that right, everybody? I want you to picture now that we're going to draw the rectangles in, not at 17/4 or 3, not at 1, the value of f of 1 or f of 1.5, but we're going to draw them in to the height of the point in the middle of the two. We're going to draw it in at the value of this case between 1 and 1.5 is 1 1/4. Does that make sense to everybody? The next one would be here, and the x value at that point would be what? Hopefully you see it's 1 3/4. The next x value will be at 2 1/4. right? If I draw that rectangle in, it'd be here, right? And the last one I would draw in would be at 2 3/4. Yeah, the F value. All right, guys, what's the width of the rectangles again? Still 4 of them, still half. And to really make you see this, I'm going to write this first. F of 1 1/4 plus F of 1 3/4 plus F of 2 1/4 plus F of 2 3/4. Now this leaves a lot of work because what do we got to do? Well, we got to plug 1 1/4 into the function and get the value for that here. All right? And again, this is why plus 2 is a kind of a pain. It's 25/16 plus 32. How about 57/16? Plus 81/16. The next one is 9/4, which is 1 plus 16. 21 plus 32. 113/16. And everyone, I'm just plugging the values, like 2 3/4 squared, right? 2.75 squared plus 2. And I get, the last one is 153/16. All right? Again, now we can summate those, add those 4 up. And I get 1/2 times 404 over 16. Everybody, hopefully you can see that you can use a little bit of cancellation. They're still both even. Everyone, I want to be clear about this. 51/4. Okay. Give me a minute. Yeah, because I took 404 divided by 2. Yep. I did a little simplification there instead of multiplying. 51/2 fourths, guys, is 12.75 for a decimal. 101 over 8 is 12.625 as a decimal. Often, the left hand and the right hand can be a pretty good instrument, and I think they're much easier to do than the midpoint. All right? Can anybody think of one more method, maybe, that would be a good estimate on this? We're not going to do it today, but I want you to at least think it in your mind. All right, and we will do this eventually. I don't want to, it gets mucky if we do too much too fast. So we can do left hands, we can do right hands, we can do midpoints, okay? And the truth is, initially the work in lesson 5.1 is all left hand or right hand. But my argument is that we also learned a formula for a trapezoid. And I see 4 trapezoids here. I see a trapezoid with a height of a half in this. I can make a trapezoid here. And then I can make a trapezoid in here. And I can make a trapezoid here. And I can make a trapezoid here. And I know the heights of all these trapezoids is a half, because you have to picture, when you look at this trapezoid, we're really thinking about it this way. Where it's a half tall, this leg is 3, this leg is 17/4. And if you don't remember your formula for trapezoid, the formula for a trapezoid was base 1 plus base 2 over 2 times h. Right? It's 2 triangles, right? But we could simplify. And again, we haven't probably done a lot of that since geometry. But we can see that this probably is the best estimate for us. And we call this a trapezoidal sum. The Riemann sum using trapezoids. What we need to do first, as we learn this, is do left hands and right hands. All right? And come comfortable with the idea.